Welcome back to our technical seminar series. Today we are starting session 4, where we move beyond installation and theory into the Gurobi basics. We will focus on the 3 pillars of any model: variables, objectives, and constraints. This session will give you the practical tools needed to construct complex models using the Gurobi Python API as part of the TwinODIS initiative. Our agenda for today is packed with technical detail. We will begin with Section 0, a review of the Gurobi basic concepts to ensure our foundation is solid. In Section 1, we will explore the global functions that simplify data management. Section 2 will cover Gurobi optimization variables in detail, specifically the advar and advars methods. We will also touch on the different types of constraints, including standard and general constraints, that Gurobi supports. Moving into the second half of the seminar, Section 3 will look at Gurobi objective functions, covering both maximization and minimization goals. Finally, we will bring everything together in Section 4 with a hands-on exercise. We will build a multi-energy optimal power flow model, or OPF, which is a real-world application of the concepts we'll cover today. To manage our models effectively, we use environments. Think of an environment as a master container that holds your global parameter settings. When you create a specific model inside an environment, Gurobi automatically creates a local copy of those global settings just for that model. This allows you to run multiple models with different behaviors simultaneously without them interfering with each other. While the Python API usually provides a default environment for convenience, understanding this container structure is vital for advanced projects where you might need to isolate different solver behaviors. The next basic concept is parameters. These are the levers that control the operation of the Gurobi solvers. You must modify these before you start the optimization process. As you can see in the diagram, parameters sit outside the model's data structure. They define how the solver should work, such as the maximum time it should spend on a problem, or how aggressive it should be with its algorithms. By changing these parameters, you can tune Gurobi to solve your specific problem faster or more accurately. Complementary to parameters are attributes. While parameters control the solver, attributes are used to query or modify the properties of the model itself. Attributes can be associated with the model as a whole, such as the final objective function value after a solve. They're also tied to specific variables, like their lower bounds, and specific constraints, like the value of the right-hand side. Essentially, if you want to know the state of your model or the result of an optimization, you check the attributes. Let's now look at a typical formulation for and optimization problem using Gurobi. In this mathematical formulation, we start with an objective function, which is subject to either minimization or maximization depending on the nature of our problem. This is subject to some constraints which define the scope of the problem and range of possible solutions. In this setup, we have some data, known beforehand, like Cij in the right-hand side of the inequalities. All this boils down to determining the Xij variables, which represent the quantities of the elements we want. These can take a range of values, and the type is specific to the respective problem. Now it's time to translate the mathematical formulation to Gurobi code in order to translate it to Python code ready for solution. To start, we define the model using the gp.model command, which sets up a model object drawn from the Gurobi. If we have determined what the problem variables are going to be, we can define them in code using either advar, which adds one variable at a time, or the plural of it, which facilitates batch addition to the model. Knowing the variables, we need to set the objective using the setObjective method. This determines the objective function, a minimizable or maximizable quantity of our choosing. Finally, similarly to the addition of variables, we can add our restrictions, the constraints, either one at a time or multiple at once. The first global function you should know is multidict, which is a lifesaver for data management. It takes a single Python dictionary where each key maps to a list of values, and it splits it apart. It returns a list of the shared keys and then a series of individual dictionaries, one for each value in your original list. This is incredibly useful for simplifying inputs like cost, capacity, and demand into parallel dictionaries that your model can easily reference. It's all about turning structured data into a format Gurobi can process instantly. Let's look closer at the mechanics of Quicksum. This function is designed to take a list of terms which can be constants, variable objects, or even existing linear and quadratic expressions, and consolidate them into a single symbolic sum. The return type is a Gurobi expression object, either a linexpr or a quadexpr. The true power of this function is efficiency. While a standard Python sum might struggle as your model grows, QuickSum is built to handle thousands of terms instantly, making it the primary tool you will use to define both your constraints and your objective functions. It is important to choose the right tool for the right job. As you can see from our efficiency table, the standard Python sum function is quite slow for symbolic expressions and should generally be avoided in Gurobi. QuickSum is our recommended sweet spot for most user code, providing a great balance of speed and readability. For truly massive sums involving thousands of terms, you might look at AD terms or linexpr for even faster performance. Looking at the examples, you can see how flexible the syntax is. Whether you are summing a simple list of terms like 2 times x plus 3 times y, or using a generator expression to sum costs across an entire range of items, the code remains clean and mathematically intuitive. The final global function for this section is read. This allows you to load an existing model directly from a file. Gurobi is intelligent enough to recognize the format based on the file extension, whether it is a human-readable .lp file or a standardized .mps file. This is a vital feature for the TwinODIS project, as it allows us to share complex models between researchers or save a snapshot of a problem to be solved later without having to rerun the entire generation script. Gurobi supports a wide variety of formats for the read function. If you want a human-readable version where you can see the variables and constraints as plain text, use the .lp format. For more compact industry-standard files, use .mps. Gurobi even supports compressed files like .zip or .gz directly. A pro tip for debugging: use model.write to save your current model as an LP file, then open it in a text editor to make sure your constraints were built exactly how you intended. You can even use wildcards like star.lp to load the first matching file in your directory. This is just a repeat of the QuickSum slide. Let's skip this one. The final global utility we'll cover in this section is read params. While we've discussed setting parameters manually in your code, sometimes you have a complex configuration that you want to reuse across many different projects. The read params function allows you to load a set of solver parameter settings directly from an external file, which must end with the .prm extension. This is an incredibly efficient way to handle performance tuning. If you've spent hours finding the perfect algorithmic settings for a specific type of problem, you can save them to a PRM file and simply read them into any new environment. This ensures reproducibility in your experiments and makes it much easier to manage batch runs where you need to test the same model under various solver configurations. Just remember, the file must follow the standard Gurobi parameter format to be recognized correctly. To see how read params works in a real-world scenario, look at the example on the slide. You might have a file named params.prm that contains specific instructions. Set the time limit to 300 seconds, apply a 1% optimality gap, and suppress the solver output. By using gp.readparams, these settings are applied globally to the default environment. This is a massive advantage for the TwinODIS project because it allows you to test dozens of different solver configurations without ever touching your core Python code. It provides a clean separation between your mathematical model and the algorithmic settings used to solve it. If you've been experimenting with many different settings, you may eventually want to start over. The function reset params clears all global modifications and restores Gurobi's default factory settings. This is particularly useful in multi-run scripts where you want a clean slate for each new test. However, a very important technical note: this only affects the default environment. If you have already created a model, that model has already snapshotted its local settings, so it will retain those even after you call reset params. To reset a specific model, you would need to rebuild it or manually adjust its local parameters. While read params handles files, set param allows you to modify a single global solver parameter directly in your code. The effect scope here is important. Calling this applies the change to all future models created in the default environment. It does not go back and change models you've already built. This is your primary tool for global performance tuning, allowing you to set custom solver behaviors like thread counts or heuristic levels right at the top of your script for total reproducibility. The final global function for parameters is write_params. This is the inverse of reading. It exports the current state of all your globally modified parameters into a .prm file. This is a best practice for long-term projects. Once you have manually tuned your solver to peak performance, you can write those settings to a file. This makes it incredibly easy to share your exact solver setup with other teams or reuse the same high-performance configuration in future runs without having to remember every single manual change you made during the debugging phase. We have now completed our look at global functions and solver parameters. We move to section 2, where we focus on the decision points of the model, optimization variables. In this section, we transition from controlling the engine to building the machine itself. We will explore how to add variables, define their types, and set the bounds that represent the physical and logical limits of our optimization problem. We are now moving into practical applications. In this section, we will look at 5 distinct optimization examples to see how real-world problems are formulated in Gurobi. Problem 1 focuses on distance minimization in a distribution network. Imagine we need to find the optimal location defined by coordinates x and y that minimizes the Euclidean distance from a fixed reference point, like the origin 0, 0. This is a classic supply chain problem for locating a depot. Problem 2 introduces a conditional production rule. In a manufacturing line, we might have a rule that says if the line is active, it must produce at least 100 units. However, if the line is inactive, production can be exactly 0. This requires what we call a binary trigger to mathematically link the on-off switch to the production volume. Continuing with our examples, problem 3 deals with maximum workload analysis. In a workforce scheduling model covering Monday through Friday, we use binary variables to track if a person is working. Our goal here is to find the maximum number of days worked by any single employee over the week, which we might use to enforce fairness or a hard workload cap. Problem 4 looks at process activation via logical conjunction. In a warehouse, a product can only be dispatched if all packaging steps like wrapping, labeling, and sealing are completed. We represent each step with a binary variable, and the final dispatch action is enabled only if all of these prerequisite variables equal 1. This is a perfect use case for Gurobis and constraints. Our final scenario is problem 5, absolute deviation penalty and pricing. In many forecasting or pricing models, you want to minimize the absolute difference between a predicted price and the actual target price, for example, $50. Because the absolute value function is nonlinear, representing it in a linear program requires specific techniques. This is often used in penalty models, L1 regularization, or when evaluating forecast accuracy within the TwinODIS framework. Gurobi provides built-in tools to handle these absolute deviations seamlessly. Everything begins with the model class. As we discussed earlier, this is the master container where your specific variables and constraints will live. For each of the 5 problems we just described, our first step in Python will be to initialize a unique model object to hold that specific mathematical logic. To build our examples, we begin with the model class, which acts as the core container for your optimization problem. Looking at the parameters table, you initialize a model using a name and an optional NV parameter. The name must be an ASCII string. You must avoid spaces or special characters because they cannot be saved in LP files, for example. AB without a space is valid, but a space B will raise an error. The NF parameter lets you pass a custom Gurobi environment, which is useful for compute servers, but as noted, beginners can skip this and use the default environment. The code snippets show exactly how simple this is. Just type m equals gp.model followed by your chosen name. Let's apply this model creation to our first 2 examples. For problem 1, the distance minimization, we start by importing model and grb from Gurobi. We then initialize our empty container with the command model equals model with the name norm_example in quotes. For problem 2, the conditional production rule, we do the exact same thing. We use our imports and initialize the container with model equals model named indicator underscore example. This initial step is identical for almost every project. It gives us the isolated workspace we need for our data. Continuing our model creation for the next set of problems. For problem 3, maximum workload analysis. We create our container by calling model equals model named max underscore example. For problem 4, process activation via logical conjunction. We set up the workspace by calling model equals model named and underscore example. Each of these real-world problems now has its own dedicated Gurobi model object, ready to hold its specific variables and constraints. And finally, for problem 5, the absolute deviation penalty in pricing. We initialize the model with the command model equals model named abs underscore example. We have now successfully created 5 separate model containers, one for each of the specific business rules we need to optimize. Before we move on to populating these empty models, let's review the structural workflow shown in the flowchart on this slide. Everything starts within the global environment, which houses your specific model. Inside that model, you must define 3 core components: your variables, your constraints, and your objective. Once those 3 pieces are set, you pass the model to the optimization engine. After the solver finishes its calculations, you extract the data during the reporting phase. This exact flowchart represents the life cycle of every Gurobi project you will ever build. Now we move to the next major component inside that model, the VR class. A VR object represents a single decision variable in a Gurobi model. As you can see in the features table, every VR is tied to one specific model, supports arithmetic operations for building constraints, and possesses various attributes. The attributes table lists the most important ones you will use. We have the LB and UB for bounds, OBJ for the objective coefficient, and V-type for the variable type. These are all read and write, meaning you can change them. Finally, we have read-only attributes like varName, and most importantly, X, which is the attribute you query to get the final value of the variable after the optimization is complete. Continuing with the VR class, we look at the methods used to interact with these variables programmatically. The first is getAter. This method allows you to query the value of a specific attribute of a Gurobi variable. For example, after an optimization run, you might want to retrieve the solution value X, or check the variable's lower bound or name. You simply call vr.getHeader and pass the attribute name. This is particularly useful when you are iterating through a large list of variables and need to extract their final states to build a business report. Conversely, if you need to modify a variable after it has been created, you use setAter. This method takes 2 parameters, the attribute name and the new value. For instance, you can change an upper bound to 0 by calling vr.setAter and passing UB and 0.0. You can also update the objective coefficient mid-script. A quick tip for Python users: while setAter is highly recommended for programmatic loops, direct Python assignments such as vr.ub equals 0.0 is also a completely valid and fast way to update these values. Now let's formally look at how we inject these variables into our model using the addVar method. This command adds a single decision variable. As you can see in the code snippets, there are multiple ways to call this. You can call it with all default arguments by simply typing model.addVar. You can specify arguments explicitly by name, such as vtype equals grb.integer and name equals y. Or you can pass the arguments strictly by position, defining the lower bound, upper bound, objective, type, and name in a specific sequential order. To clarify exactly what those parameters do, let's break them down. LB and UB set the lower and upper bounds. If you don't specify them, Gurobi automatically assumes a lower bound of 0 and an infinite upper bound. OBJ defines the variable's coefficient in the objective function. VType determines the mathematical nature of the variable, whether it is continuous, binary, or integer. Finally, name assigns an ASCII string label. When you execute this method, It successfully returns a Gurobi VR object, which you will then use to build the mathematical expressions that define your problem. Adding variables one by one is fine for small test cases, but for large-scale applications in the TwinODIS project, we rely on addvars. This method generates multiple decision variables simultaneously. The first parameter, indices, defines the shape of your variable set. For example, passing 3, 4, and 5 creates a three-dimensional array of 60 variables in one single line. You can also pass a Python list of specific tuples to create variables only for valid roots in a network. You can even pass lists or dictionaries for the bounds or objective coefficients, allowing you to assign different costs or limits to each variable dynamically as they are generated. To finish our look at the addvars method, let's focus on its return type and purpose. When you call this method, it doesn't just return a standard Python list. It returns a gurobi.tupeldict. This is a specialized dictionary where each key corresponds to the index you provided, and each value is the corresponding VAR object. The true purpose of this method is to create this tupeldict efficiently using shared or individual settings for the bounds, types, and names across hundreds or thousands of variables at once. It is the workhorse of any large-scale TwinODIS model. Let's return to our 5 examples and see how these variables are actually declared in code. For problem 1, the distance minimization, we need coordinates and a distance metric. We can define them individually. X equals model.addvar, Y equals model.addvar, and D equals model.addvar. Alternatively, we can group the coordinates into a vector using point equals model.addvars2. For problem 2, the conditional production rule, we need 2 distinct types of variables. We define the trigger. Activate equals model.addvar with vtype equals grb.binary. Then we define the continuous production amount. Produced equals model.addvar. This gives us the exact mathematical pieces we need to build our if-then rule later. Moving to the next 2 problems. For problem 3, maximum workload analysis, we use addvars to create a schedule array. Days equals model.addvars4 with vtype equals grb.binary. We also add a continuous variable, max_days equals model.addvar, which will eventually hold our calculated maximum. For problem 4, process activation via logical conjunction, we need a variable for each packaging step. We create an array, pack_steps equals model.addvars, 3, setting the type to binary. We then define the final output state, output equals model.addvar, also set as a binary variable. Finally, for problem 5, the absolute deviation penalty. We are working with a known constant target, so we define actual equals 50. We then define 3 continuous variables. Predicted equals model.addvar for the algorithm's guess. Diff equals model.addvar to hold the raw mathematical difference. And error equals model.addvar, which we will strictly constrain to be the absolute value of that difference. By separating the difference from the absolute error into 2 variables, we provide Gurobi with the exact structure it needs to apply its built-in nonlinear constraints. With our variables fully declared across all 5 examples, we have completed the first major internal step of our model build. As a reminder, looking at our workflow flowchart, we have established the environment, initialized the model, and defined the variables. The next logical step in this sequence is to define the constraints. These are the mathematical rules that will connect our variables together, forcing the distance to match the coordinates, or forcing the production to respect the binary activate trigger. We will cover this next. We now move to the constraints. The primary command for adding a single rule to your model is addConstr. This method takes a temporary constraint expression, created using standard Python math syntax, and an optional ASCII name. Looking at the code examples, you can see how incredibly flexible this is. You can add a simple linear constraint like model.addConstr, x plus y is less than or equal to 2.0. You can add a quadratic constraint by multiplying variables. X times x plus y times y is less than or equal to 4.0. You can even use it for advanced general constraints such as setting a variable, z equal to the mathematical end of x and y, or creating indicator constraints with the implies operator. Regardless of the mathematical complexity, you use this single unified method to insert the rule into your model. Let's look at what the addConstr method returns. Depending on the math you passed into it, Gurobi will automatically identify and return a specific constraint object. It will return a standard constr for linear equations, a qconstr for quadratic expressions, or matrix-specific objects if you are using advanced NumPy arrays. The true purpose of this method is to allow you to build rules using intuitive Python operator overloading. This means you can type the math into your script almost exactly as you would write it on a whiteboard. Just remember, the name parameter must strictly use ASCII characters without spaces to avoid errors when exporting your model for debugging. Just as we used addvars to build arrays of decisions, we use the addConstrs method to build arrays of rules. This method leverages a Python generator expression. Instead of writing a standard for loop that calls addConstr multiple times, you write a single, elegant line. For example, the first code snippet says, model.addConstr sum of x is less than or equal to capacity bracket I for I in range 5. It handles linear, quadratic, and general constraints equally well. If you provide a base name, Gurobi will automatically index the constraint names for you, like name bracket 0 and name bracket 1, keeping your solver logs perfectly organized. When you execute addConstrs, it returns a gurobi.tupeldict. This dictionary contains all the newly created constraint objects perfectly indexed by the values you used in your generator expression. The primary purpose of this function is computational efficiency and code compactness. When you are building a model for the TwinODIS project with thousands of supply nodes or time periods, writing a single Pythonic generator is significantly faster for the Python interpreter to process than a standard loop. It is the absolute best practice for handling indexed variables and highly structured constraint patterns. While addConstr can handle many logical expressions, Gurobi also provides explicit methods for general constraints such as addGenConstraints. This method forces a specific result variable to be exactly equal to the maximum value from a given list of variables, plus an optional constant. You pass the raceVar, which is the result variable, followed by the vars list. The slide shows 3 different ways to write this in Python. You can use the explicit addGenConstmax method, or you can use the more modern max_helper function directly inside a standard addConstr call. Both approaches tell the solver to handle this nonlinear maximum logic efficiently under the hood. To wrap up the max constraint, when you call this method, Gurobi returns a specialized object of type grb.genConstr_max. The fundamental purpose of this function is to define a nonlinear rule where a specific result variable is strictly equal to the maximum value found within a list of input variables. This is incredibly useful for modeling worst-case scenarios or defining dynamic capacity limits in our TwinODIS environments without having to write complex multi-line linear workarounds. Next, we have the absolute value constraint. In mathematical modeling, minimizing the absolute difference is common, especially when evaluating forecast errors. You add this using add-gen-constr-abs. It takes a raceVar, the variable that will store the positive absolute value, and an argvar, whose absolute value is being taken. Just like before, Gurobi offers a highly readable overloaded form. You can simply write model.addConstr, and inside it x5 equals abs underscore of x1. This keeps your code looking exactly like standard algebra. When executed, this returns a grb.genConstr_abs object. Its explicit purpose is to mathematically enforce that the result variable equals the absolute magnitude of the argument variable. A vital tip to remember here: because it is an absolute value, the raceVar must naturally be non-negative. Gurobi enforces this implicitly, so you don't need to add a separate constraint to prevent it from going below 0. This is exactly what we use for penalty models and L1 norms and pricing algorithms. Moving on to logical operators, we have addGenConstr. This allows us to link multiple yes or no decisions together. This constraint takes a result variable and a list of input binary variables. If you want a specific process to only turn on when 3 separate subprocesses are completely finished, you use this function. Looking at the code, you can use the explicit method or the elegant overloaded form model.add_const x5 equals an underscore, passing a list of x1, x3, and x4. This is how we handled the process activation warehouse scenario we discussed earlier. This function returns a grb.genConst and object. Its mathematical purpose is straightforward. The result variable is set to 1 if and only if every single variable in the input list is also equal to 1. Otherwise, it is 0. There is an important under-the-hood behavior to note here. Any variable you include in an AND constraint will be automatically treated as a binary variable by the solver, even if you accidentally declared it as continuous earlier in your script. Gurobi is smart enough to know that logical conjunction only works with true-false statements. We now look at the norm constraint. You add this using add_genConst. This constraint is incredibly powerful for spatial modeling. In the parameter table, we see it requires a race var to store the result, a vars list representing the input vector, and the which parameter. The which parameter lets you choose the exact type of norm, 0 for the number of non-zero elements, 1 for the Manhattan norm, 2 for the standard Euclidean distance, or grb.infinity for the maximum norm. The code snippet shows a simple example of calculating the Euclidean norm of 3 variables, binding the result directly to the variable x_race. When you run this function, Gurobi returns a grb.genConst_norm object. Its mathematical purpose is to constrain your result variable to exactly equal the calculated vector, norm of the specified input variables. One critical structural tip here. The variables in your input list must be entirely unique, cannot have duplicate variables in the vector. As we mentioned earlier, this constraint is the exact tool we use to calculate the geometric distance for our distance minimization distribution network problem. Moving on to one of the most frequently used logical constraints in scheduling and manufacturing, the indicator constraint. Added using add_genConst, this function returns either a standard genConst or a matrix-friendly mgenConst. Its purpose is to create a conditional if-then rule, mathematically. It states, if this binary variable equals a specific value like 1, then this subsequent linear constraint must hold true. Otherwise, the constraint is completely ignored by the solver. This is the exact mechanism we use for our conditional production rule. Let's break down the parameters required to build this if-then logic first. You need the bin_var, the binary indicator variable acting as your physical switch. Next is the bin_val, which is the value typically true or one that actually triggers the rule. Then you provide the then statement using the LCHES for the left-hand side expression, the sense for the equality or inequality direction, and the RS for the right-hand side limit. Finally, as always, you can provide an optional ASCII name for cleaner debugging. To see this in code, look at the examples on this slide. You can define it explicitly by passing all the arguments separated by commas. However, Gurobi also supports a highly readable overloaded form using the Python right-shift operator, the double greater than sign. You simply write model.addConst inside parentheses x7 equals 1, implies x1 plus 2 times x3 plus x4 equals 1.0. So it reads exactly like formal mathematical logic. Note that whatever variable you use as the trigger will be automatically forced to act as a binary variable by the engine, regardless of its original type. Now we bring everything together and build the constraints for our first 2 examples. For problem 1, distance minimization, we need to mathematically tie the distance variable d to the x and y coordinates. We do this by implementing a NORM constraint with order 2, which is the standard L2 norm. The code reads model.agenConst, passing d as the result, our point vector as the input, and 2 for Euclidean distance. For problem 2, the conditional production rule, we need our binary trigger. We mathematically link the active state to the produced volume using an indicator constraint. The code reads model.agenConst, stating that if activate is true, then produced must be grb.greater_equal to 100. Move into the constraints for our next two problems. For problem 3, maximum workload analysis, we need to find the peak number of days worked. We simply use the max constraint. The code is model.add_max, setting max_days as the result, and passing the list of all individual days worked across the week. For problem 4, process activation, the warehouse dispatch only happens if all packaging steps are done. This is a perfect fit for the and constraint. We write model.addConstraint, setting output as the result, and passing the list of our 3 binary pack_steps. Finally, for problem 5, the absolute deviation penalty. As we set up earlier, we cannot take the absolute value of an equation directly inside the absolute constraint. We have to do it in 2 steps. First, we define the raw mathematical difference using a standard constraint. Model.addConstr diff equals predicted minus actual. Once diff is defined, we apply the ABS constraint model.add-gen-constr-abs. Passing error is the result and diff is the input. This 2-step process correctly bounds our error variable so that the optimizer can accurately minimize it later. We have now successfully defined our variables and built our constraints across all 5 examples. Let's look back at our workflow flowchart. We are almost finished with the core model assembly. The only component missing inside our model container is the objective. The objective is the single mathematical goal that guides the solver through the feasible region we just created. Let's look at how we define that target. To set the goal for the engine, we use the setObjective method. This method takes 2 arguments. First is the expression, which is the linear or quadratic formula you are evaluating. In the example on the slide, we use our favorite utility function, gp.quicksum, to sum up the costs times the variables. The second argument is the sense. You must tell Gurobi whether to push this mathematical sum as high as possible using grb.maximize, or as low as possible using grb.minimize. Once this line of code is executed, your mathematical model is fully built and ready for the engine to solve. Now we set the objectives for our first 2 examples. For problem 1, distance minimization, our goal is simply to minimize the calculated distance variable d. We write model.set, objective, passing d, and grb.minimize. For problem 2, the conditional production rule, we want to maximize the total produced volume. We write model.setObjective, passing produced, and grb.maximize. With these 2 simple lines, Gurobi knows exactly what metric determines the absolute best solution. Move into the objectives for the next 2 problems. For problem 3, maximum workload analysis, we want to enforce fairness across the schedule by minimizing the peak workload. We set the objective to minimize the max_days variable. For problem 4, process activation, our objective is to maximize the final output state to ensure the highest possible volume of shipping. The Python code for both is straightforward directly, passing the target variable and the required optimization sense to the solver. For our final scenario, problem 5, the absolute deviation penalty, our mathematical target here is strict, minimize the total forecast error. We write model.setObjective, passing our constrained error variable, and grb.minimize. By completing this final step, all 5 of our conceptual models are mathematically complete, from the environment initialization, through the variables and constraints, all the way down to the objective function. We have now reached section 4 of our session. We're going to transition from these isolated conceptual examples into a comprehensive real-world case study. We will be building a multi-energy optimal power flow model, or OPF. This hands-on exercise will bring together everything we've learned today about parameter control, TupleDics, general constraints, and objective functions into a single, cohesive Python script. Let's define the context for a hands-on problem. We are managing an energy transportation problem across a national grid. We are dealing with 2 distinct energy types simultaneously, electricity and hydrogen. Our supply originates from 2 nodes, Detroit and Denver. We must meet the energy demand at three specific destination cities: Boston, New York, and Seattle. The physical reality of our network is governed by strict line capacity constraints, which cap the physical flow on any given route between 100 and 120 megawatts. Our overarching objective is to minimize the total energy delivery cost across the entire network while strictly meeting all demand requirements. Let's open our Python environments and start building this OPF model. To fully understand the structure of our model, let's visualize the network geographically. On this slide, we begin with our two supply nodes, Detroit and Denver. These two cities are the origins of our energy flow, responsible for supplying both the electricity and hydrogen that must be routed to our demand centers. First, let's look at the outgoing routes from Detroit. As you can see, the transmission lines from this node have specific physical limitations. The route to Boston has a maximum capacity of 100 megawatts. The route to New York is capped at 80 megawatts. And the long-distance route to Seattle can handle up to 120 megawatts. Next, we map the outgoing lines from our second supply node, Denver. The infrastructure originating from Denver is more uniform. The transmission routes connecting Denver to Boston, New York, and Seattle all have a maximum capacity of 120 megawatts each. To build our Python script, we need to translate that geographic map into a structured format. This slide summarizes all 6 possible transmission routes and their respective capacities in a clean table. This list of origins, destinations, and MW limits is exactly the kind of structured data we will feed into Gurobi's multi-dict function to automatically generate the bounds for our flow variables. Now we define our formal model elements before we start coding. Variables. We will use a 3D array, flow bracket E, I, J. This represents the amount of energy type E sent from node I to node J. Constraints. We have two main rules. First, the arc capacity rule ensures the total flow across each route is less than or equal to its limit. Second, we have the critical flow balance rule. This ensures that the inflow plus local generation exactly equals the outflow plus local demand at every single node for each energy type. Objective. Our goal is to minimize the total delivery cost across all arcs and energy types. To keep our math simple, we use a sign convention. A positive inflow value indicates a supply node, while a negative inflow value indicates a demand node. Next, we need to map out the economic realities of our network. This slide visualizes the delivery costs specifically for our first energy type, electricity. From Detroit, sending electricity costs 10 euros per megawatt to Boston, 20 to New York, and 60 to Seattle. From Denver, the costs are 20, 20, and 80 euros respectively. The optimizer will use these exact cost coefficients in our objective function to determine the absolute cheapest paths for the electrical load. We also have our second energy type, hydrogen. Hydrogen transportation has a completely different cost structure and physical reality. Looking at the map, from Detroit it costs 40 euros to Boston, 40 to New York, and 30 to Seattle. From Denver it's 60, 70, and 30 euros. Because these two energy types share the same physical infrastructure limits defined earlier, the solver must constantly balance the cheap electricity routes against the expensive hydrogen routes to find the global minimum cost. Just as we did with our line capacities, we must structure this complex cost data for our Python script. This slide displays the comprehensive cost tables for both electricity and hydrogen. By organizing this data into structured dictionaries using the multi-dict global function we learned about in section 1, we can effortlessly map these cost coefficients to our flow variables. This approach ensures our code remains perfectly scalable, even if we decide to add 50 more cities or a new energy type later on. After defining the variables, adding the capacity and flow balance constraints, and setting our objective, we run the optimize command. Here we see the final output. The solver successfully found an optimal solution with a total objective value of exactly 5,500 euros. The tables on the screen show the precise flow in megawatts for both electricity and hydrogen across the active routes. Instead of relying on manual estimates, we now have a mathematically proven, fully optimal dispatch schedule. Let's interpret what Gurobi actually decided. For the electricity routing, the solver correctly prioritized the lowest cost paths, maxing out the cheap €10 route from Detroit to Boston and relying on Denver to handle New York. For hydrogen routing, which is generally more expensive, the routes are more spread out. Detroit handles the East Coast demand, while Denver covers part of Boston and all of Seattle to respect the shared arc capacities. Let's interpret what Gurobi actually decided. For the electricity routing, the solver correctly prioritized the lowest cost paths, maxing out the cheap €10 route from Detroit to Boston and relying on Denver to handle New York. For hydrogen routing, which is generally more expensive, the routes are more spread out. Detroit handles the East Coast demand, while Denver covers part of Boston and all of Seattle to respect the shared arc capacities. That brings us to the end of Session 4. We've covered variables, objectives, standard linear constraints, and highly specialized general constraints, putting it all together in a powerful multi-energy model. I've included links here to the official Gurobi documentation for general constraints and the Model Python API for your further reading. Thank you for following along with this TwinODIS presentation, and I look forward to seeing the complex optimization models you build next.